Imagine you were in your spaceship in the middle of interstellar space, and suddenly an immense force started pulling you toward a single point in space, and nothing you did helped stop this immense, scary force. It seems like a nightmare, but to better understand the idea, we need to understand a little more about black holes. Imagine you were in your spaceship in the middle of interstellar space, and suddenly an immense force started pulling you toward a single point in space, and nothing you did helped stop this immense, scary force. It seems like a nightmare, but to better understand the idea, we need to understand a little more about black holes. Wait, what is a black hole? By definition, a black hole is a region in space-time that lets nothing, not even light, escape. The theory of general relativity predicts that a sufficiently compacted mass point to form space-time, to form a black hole. The idea of objects whose gravitational field was so immense that it wouldn't let light escape was considered for the first time in the 18th century by John Michell and Laplace. The first general relativity solution that characterized black holes was found by Schwarzschild in 1916. But the question is, how do you observe an object that emits no light and absorbs all the light that hits it? For this, it is necessary to observe the black hole's interaction with the matter around it or with electromagnetic radiation like light. The matter falling into a black hole's gravitational field can create an accretion disk that is heated by friction, forming one of the brightest things in the universe. Although the name is also misleading. A black hole isn't like a hole in the middle of the universe. It is an immense, extremely compacted spherical point. The idea that a black hole sucks in everything around it also only applies to the event horizon, a special area around a black hole. Outside the event horizon, the black hole's gravitational attraction is the same as that of a body of the same mass. In other words, a black hole with the mass of Earth, although extremely smaller than Earth, would have more or less the same gravitational field. Returning to the event horizon, everything that passes through the event horizon has no return. That is, everything that passes the event horizon ends up being captured by the black hole and can no longer get out. As happens with light, if light passes the event horizon, it can no longer return. This is what characterizes the black hole. If you manage to enter the event horizon, your body would be stretched in such a way that no end of your body could find a path that didn't lead into the black hole itself. To a distant observer, a person falling into a black hole would be slowed down in time. So, the person would see them falling and stopping. It would take infinitely long to pass the event horizon until at some point they would stop and then start to fade away. But what if you were the person falling inside a black hole? What wonderful phenomena would happen to you? Unfortunately, nothing strange would happen. For anyone falling toward the event horizon, no strange effects would be noticed. Let's say the person had a watch in their hand and survived the destructive gravitational force of a black hole. They wouldn't even notice they passed the event horizon. But not to say that black holes don't have anything cool, because I think it's one of the things that causes the most fear in the universe. I don't know, like bumping into a black hole and being destroyed. Whatever happens, there's a region where photons enter into orbit around the black hole. That is, if you manage to stand still right in that region and look forward, you would see the back of your own body. But if you went a little lower than this region, there would be no return. You'd be captured too. But since the universe is full of aberrations, can I create my own black hole a home? Or rather, how does a black hole form? In case you gather a huge amount of energy, who knows? It is easier to observe the formation of black holes in space by observing supernovae. When the fuel of a sufficiently large star runs out, the star collapses and ends up becoming super dense. Its outermost material begins to be sucked in with such speed that gravity cannot support all the energy being released, and the star ends up exploding in just a second. This explosion is 100 times greater than all the energy the sun will produce in its history. What remains of this explosion is a black hole. And so we ended up learning a little about black holes. In case you haven't seen the first video of the channel that I posted, I think it's worth watching. And that's it. If you enjoyed it, please leave a like, subscribe to the channel, and share. Thanks for watching.